Hi guys, welcome to Easy Math.
In this video, we are going to see the corollary. This is also an important question. Homomorphism of G into G bar with the kernel K phi is an isomorphism of G into G bar if and only if K phi is equal to singleton E. What's given? A homomorphism phi from G to G bar is with the kernel K phi. What's the definition of kernel? Set for x in G such that phi of x is equal to E bar, where E bar is the identity element of G bar, right? In this corollary, you have to prove that isomorphism of G into G bar if and only if K phi is equal to singleton E. First, we have to assume that phi is an isomorphism of G into G bar. Phi is an isomorphism of G into G bar means, already we know the definition of isomorphism. What is that? It is bijective and homomorphism condition, right? What is bijective? It is 1 1 on 2. Therefore, the isomorphism means 1 1 on 2 and the homomorphism condition. But in this corollary, they mention it as just into. No need to bother about the on 2 condition. Okay, so no need to bother about the on 2 condition. You have to prove that kernel is equal to singleton E. Since phi is a group homomorphism, the identity element of G, that is E, is mapped into the identity element of G bar, that is the E bar. Hence, phi of E is equal to E bar. Hence, phi of E is equal to E bar. Name it as equation number 1. Now, let us take one element x from this kernel. Then, phi of x is equal to E bar, because the elements in the kernel are always defined as phi of x is equal to E bar. So, phi of x is equal to E bar, name it as equation 2. From equation 1 and 2, we are getting the right hand sides as same. Therefore, the left hand sides are also equal. Phi of x is equal to phi of E. Since phi is an isomorphism, it satisfies the 1 1 condition, right? Clearly, phi is 1 1. Therefore, if phi of x is equal to phi of E means x is equal to E for all x in G. Hence, K phi is equal to, that is kernel K phi is equal to the singleton element E. Next, converse part. Conversely, assume that kernel K phi is equal to singleton E. You have to prove that phi is an isomorphism of G into G bar. You have to remember, in this corollary, they are mentioning G into G bar. Therefore, no need to prove the onto condition. Okay. Since phi is a homomorphism, it is enough to prove that phi is 1 1. Since phi is a homomorphism, it is enough to prove phi is 1 1, because they are mentioning G into G bar. No need to prove the onto condition, right? What we want to prove for 1 1 condition? Let us take pi of x is equal to pi of y. By post multiplying pi of y, the whole inverse on both sides, we are getting pi of x into pi of y, the whole inverse is equal to pi of y into pi of y, the whole inverse. Since by the previous lemma, pi of y, the whole inverse can be written as pi of y inverse. Pi of y into pi of y, the whole inverse is equal to E bar, since this element belongs to the group G bar, right? Therefore, phi of x into phi of y bar is equal to E bar. Since phi is a homomorphism, this can be written as phi of x into y inverse is equal to E bar. According to the definition of the kernel K, this element xy inverse belongs to the kernel, that is kernel K phi. Xy inverse belongs to K phi. We assume that K phi is equal to singleton E. Therefore, xy inverse is equal to E. Hence, x is equal to y. By bringing this y to the other side, we are getting x is equal to y. Therefore, phi is 1 1, because we are assuming phi of x is equal to phi of y implies phi x is equal to y. Therefore, phi is 1 1. Hence, phi is an isomorphism of G into G bar. Hence, the corollary.
Thank you for watching. Don't forget to like, share and subscribe. Bye guys.